So in this video, what we're going to take a look at is what's called slope-intercept form. And what you will find is that slope-intercept form is going to be very similar to just what we've been learning about in terms of what we called the intercept form. Okay, and remember, intercept form said y equals bx plus a, where b was our rate of change and a was our y-intercept, or our starting value. Okay, so again, you will see that there are some similarities between the slope-intercept form and the intercept form in this lesson. Now, before we get started, I would like for you to try the warm-up and look at how these two graphs that you're given are similar and how they are different. So pause the video, complete the warm-up, and then unpause it and we'll go over it. So hopefully you've noticed some similarities and some differences in these two graphs. So some similarities that I noticed is that both graphs appear to be linear in shape. What's that mean? That means, they both appear to be going in a straight line. Another similarity is that they both appear to have a positive rate of change. How do I know that? Because both lines in this case are increasing, which means that as the x values increase, the y values increase. Now, in terms of being different, one thing that stands out to me right away is that the graph on the left is a discrete function. The graph on the right is a continuous function. So discrete versus continuous. And remember, a continuous function shows up when your data points can be counted as decimals. A lot of times, if you think about it, if you're measuring time, that is where you can measure in hours, minutes, seconds, milliseconds, so you can constantly measure time. Whereas the graph on the left, when it's discrete, that could represent something where you're measuring sort of the number of the amount of daylight in one day. And why that is discrete is because when we're talking about the amount of daylight, we're saying in day one of the year there's there's such amount of light. In day 2 and day 3, you cannot have 0.25 days. Okay, when you're talking about the amount of daylight, or if you're talking about the amount of deer, right? You can't have half of a deer. You can't have 4.5 deer, because that means that one of your deer is chopped in half. So that deer is not counted. So when your data is measured in a sort of where your data has to be whole numbers, that's when you're going to have a discrete function. And the big difference, how you can tell, is a continuous function is going to connect all its points with a line. A discrete function is not. And then one other difference you might notice is that the graph on the left is not a perfectly straight line. It's not perfect. But the graph on the right is a perfect straight line. So what I'll put here is perfect versus non-perfect linear line. All right, and so we're going to talk about why that might be. So let's jump into our lesson. So when you plot real-world data, you're often going to see linear patterns. However, when you're plotting real-world data, what you're going to find is data points rarely fall into a perfectly straight line. All right, so they rarely fall exactly on a line. And our question is, if we are going to, if we want to connect these points, how do we tell if our line that we draw or we use is a good model? Again, so the question is, how can we tell if a particular line is a good model for our data? And so what we're going to do is we're going to talk about how to find that line. And one of the best ways to figure out if the line that is shown is a good representation or a good model for the data is if the line shows the general direction of the data and if there are about the same number of points above the line as below the line. And when you have a line where it has the same general direction, meaning positive or negative, increasing or decreasing, and the same number or a similar number of points fall above the line as below the line, you get what you call a line of best fit or a line of fit. So we're going to take a look at some of our examples and talk about how to come up with this line. We're going to use Desmos to come up with this line, and then we're going to talk about what this slope-intercept form is. So let's take a look at example A. So in example A, it says Papano's Pizza wants to offer an extra large pizza. To determine the price of the new 16-inch pizza, they decide to use the pricing of their current 4 sizes to find a relationship between the diameter of the pizza and the price. So essentially what they want to do is they want to use this information that they have about their current pizzas to figure out how much their price for an extra large pizza should be. So what we're going to do, let's jump to Desmos, and we're going to plot these points on a graph. So again, you should definitely follow along with how to do this, because you're going to want to know how to make a table, especially if you have to take an end of course test. So 7 and 3.75, 10 and 6.99, and then we have 12 and 9.99, and we have 14 and 10.99. So we get these points. Let's go ahead and see our points on our graph. So there they are. And what we're going to do is we need to figure out a line that sort of represents those points. So what we've learned about in the past is how to find the equation of a line. We know that the rate of change is represented by, or the relationship between x and y is represented by our slope. So let's take the information that we have, and let's find the slope of a line that would pass through this point and this point. Because if we can find a slope slope of a line that passes through those 2 points, then we've found a relationship between the price and the diameter. So remember, slope is change in y divided by change in x. Change in y would be 10.99 minus 3.75 divided by 14 minus 7. Remember, it's y2 minus y1 divided by x2 minus x1. So we have 10.99 minus 3.75. That is 7.24 divided by 7, which gives us 1.03. All right, and so what that means is that, remember, change in y over change in x, that means that it is basically $1.03 per inch for this pizza. All right, so that's our slope of a line that passes through the personal size and the large size pizza. So let's go ahead and take a look at what happens when we graph this line. So if we type in y equals 1.03x, we should see that we get this line right here. And what you will notice is, well, it doesn't seem to be a very good representation of this data, because if you look at this, all the points lie underneath this line. And again, we said that if we want to find a good representation of some data, you want an equal number of points above the line and an equal number of points below the line. So what this means is that we probably need to adjust our value for our y-intercept. So let's put b here. All right, so actually let's do this, bx plus a, because that is what intercept form is. It's bx plus a. So let's add this slider, and if we look at this, let's adjust where we want this line to intersect the y-axis. So if we do this, it looks like we need to move it down, and we want to sort of have an equal number of points above and below this line. All right, so if we look at that, we get maybe negative 3.2, negative 3.4. Again, let's go with negative 3.3. All right, so you have 2 points sort of above or on and 2 points below the line. So what this tells us is that in order to get a good representation of this data, it might be useful to say that our y-intercept is negative 3.3. So if we type that in, minus 3.3, and we get our line that we used our slider to come up with. All right, so we have, and for an equation of this, y equals 1.03x minus 3.3. So that is an equation that we came up with to represent this data. So this is our line of fit. Now, a linear equation, okay, actually let's back up. So real quick, let's determine the price of a 16-inch pizza. So if we use our equation, y equals 1.03 times 16 minus 3.3. Again, why do we plug 16 in here? Because 16 is our x-axis, or x coordinates. So we have 1.03 times 16 minus 3.3, which gives us $13.18. So if we're using this relationship that we've discovered with our line of fit, we would say that they should charge for an extra large pizza that is 16 inches in diameter. They should charge $13.18 to fall in line with their current prices. Now, a linear equation written in this form, y equals mx plus b, which is what we have, y equals 1.03x minus 3.3, is written in slope-intercept form. So what you'll notice is that slope-intercept form looks exactly like intercept form. Now, the difference is the use of letters and which letter represents what. So if you see y equals mx plus b, you would notice that it looks very similar to y equals a plus bx. And it says, how is intercept form like this? Well, they both represent, so a and b tell us, actually let's clarify this. A, and we'll say this is intercept form, and B, that's in our slope-intercept form, represent the y-intercept. Okay, so both equations, both forms tell us what our y-intercept is. And then B in intercept form and M in slope-intercept form both tell us our slope slash rate of change. So they are similar. But the difference is, that the slope-intercept form uses a different letter for slope and the y-intercept. So the question that we have is, does the constant b in intercept form represent the same thing in both forms? And the answer is no. Okay. In slope-intercept form, and again, I'm just going to abbreviate that SIF, b is equal to the y-intercept. In intercept form, b is equal to the rate of change, or slope. Okay? Starting today, we're going to refer to everything in slope-intercept form. Y equals mx plus b, which I believe a lot of us have been familiar with in 8th grade. So let's take a look at this investigation. So when you drive around a big city, you might wonder, how is the distance between two locations related to the time it takes to travel between them? Okay, how does Google Maps figure out that time? So there's varying speeds and amounts of traffic, and this might not be an easy relationship to model. So what we're going to do is I want you to take some time to look up a map and some driving directions, and I want you to find a route between two suburbs, and I want you to do this 6 times, all right? And then I want you to record your driving distance and time in a table on Desmos. So I know this says Chicago. If you want to do this on your own and do Columbus, since that's the city that we live in, go ahead. If not, I have gone ahead and looked up the distance and the time it takes to travel to some places in Chicago. So you have Oaklawn, Skokie, Oaklawn to Skokie, Bucktown to Hyde Park, Evanston to Park Ridge, Wilmette to Burbank, Melrose Park to Maywood, Cicero to Clearing. Again, you might not know where these cities are. These are all suburbs of Chicago. And then you have your distance and your time. So we're going to put these in a table on Desmos, but before we do that, let's define our independent and dependent variables. So remember, our independent variable is always going to be our x value, and our dependent is always going to be our y value. So the time is dependent on the amount of on the distance that we have to travel. So in this case, our independent variable is going to be our distance, and our dependent variable is going to be our time. All right, so let's go ahead and plot these points on our graph. So I'm going to jump over to Desmos and get rid of this table here. And so add another table. So we had 13 and 29. We had 12.7 and 21. We had 9.8 and 23. We had 31.5 and 47. And then we had 2.6 and 7. And finally 5.9 and 18. Okay, so again, remember, x is our distance and y is our time. Let's adjust our window so we can see everything. There we go. And I'm going to, we won't copy this into our notes yet. So I'm going to jump back over to our notes. And so it says plot your data on the calculator, sketch the plot on your paper. We're going to insert our picture here in a minute. Now, what I want you to do, we're going to do some stuff on Desmos here, is I want you to type in the equation y equals mx plus b on line 2 in your Desmos, and then you're going to see something that pops up and says add slider, and I want you to hit all, okay? And then what I want you to do is I want you to use those sliders to create a line that you think fits the data, and then I want you to write down that equation, or what your slope and y-intercept is, under here, okay? So if we jump back over here, again, we're going to type in y equals mx plus b. And then you see where it says add slider, we're going to hit all. And then you'll see a line pop up. And then you'll see where it says m equals 1, b equals 1. And so what we want to do is we want to come up with an equation of a line that might represent this data well. So remember, so it looks like we maybe need to adjust this. So let's make this a little bit steeper. And what we want to do is we want to get this to where we have an equation where it is, an equal number of lines or points above and below. All right, so let's see. It's a little bit harder to do. I want 1.4. I saw 1.4 looked good. Since my finger is making it jump, we're going to go ahead and just type in 1.4. Okay, so if you look at that, you'll see that you have a line that's increasing just like our data points, and you see that there are 3 points below the blue line and 3 points above the blue line. And if you look at this, you see that maybe 7.2 is a good number, maybe 7. It's being difficult here for me to be able to get an exact number here, so I'm just going to type in 7 there. All right. Again, your value for B, your value for M might be a little different than mine, okay? But I'm going to use 1.4 and 7. So if we wanted to, and I'm going to go ahead and I'm going to screenshot this picture, or this graph, jump back over here, and I'm going to drag this into here, all right? So we have this, graph, this plot of our equation. So I'm going to make note of what our slope and our y-intercept is. So our slope was 1.4. So m was equal to 1.4. And our y-intercept, b, was equal to 7. So that gives us an equation of y equals 1.4x plus 7. All right? So then if you jump down to step 5, it says use the slope m that you found in step 4 to graph the equation y equals mx on your calculator. Y is the line parallel to the line the points indicated, and is the line too low or too high to fit the data. So if we jump back over here, we're just going to take a look at this. What happens if we type in the equation y equals 1.4x? And you get this black line right there. And what you notice is that all the points fall above that line. So that line is too low. It's not high enough, which we know because we said, to get a good line, we needed our y-intercept to be 7. And what the question says is, why is this line parallel to the line that the points indicate? And maybe you've heard this before, maybe you haven't, but whenever two lines are parallel, that means what we know about these lines is parallel lines have the same slope. Okay, so anytime that you have two lines with the same slope, you know that they're going to be parallel. And in this case, when it asked is the line too high or too low, it was too low to fit the data. So in step 4, everyone started with a visual model, and that went through 2 points. In your group, we compared all of our final lines. Probably if you did this and we compared all of our lines, we probably would find out that our value for M and our value for B were a little different. So it says, do you think a line of fit must go through at least 2 data points? All right. So in this case, does a line of fit need to go through 2 data points? The answer is no. So if we answer this, okay, a line of fit does not have to pass through 2 points. It's okay if they do, but again, our goal is we want to have an equal number of points above and below the line that we draw in. And then it says, is any one line a better fit than the others? Okay, and what that means is that the way that one line is better than the other is if they have an equal number of dots above and below. So we'll say yes, lines with equal number of points above and below are better. Now, I do want to tell you, there are going to be times when you cannot get equal number of points above and below, okay? Sometimes it just does not happen. So do not worry about it if you cannot. Now, what I want to do is, in this case, what I want you to make sure you know is that we have estimated what this line of best fit is. We were dragging a line and whatnot, and what we want to do is we want to be able to find the exact line of best fit. Okay, the exact line of fit. And in order to do that, what we're going to do is we are going to use Desmos, and it's going to tell us exactly what our line of fit is. So what we're going to do is we're going to jump back to Desmos, and we're going to get rid of all of our equations, and we're going to say, we're going to type in this. In order to find out the exact line of best fit, you're going to have to use y sub 1 and x sub 1 because that is what is in our table, so we want to use those points. So we're going to go y sub 1. See how it tells you it's using those elements in that list, and we want it to be we want to put an approximate symbol, is approximately a x sub 1 plus b. Now, what I want you to, first of all, what I want you to understand is I have to use a here instead of m because Desmos does not recognize m in this form. Okay, so a is the same thing as m in this case. So if you look at this, it tells you what a is and it tells you what b is. It tells you a is 1.2731. It tells you b is equal to 8.146. So we're going to use those numbers. We're going to write those down, and we have, so the exact line of fit for this equation is y equals 1.2731, and then we'll round that, 2731, we'll say 1.27 x plus 8.15. Okay, so that is the exact line of best fit. Desmos has a way to find the line of fit for you And I would recommend that you use that when you're being asked to find your line of fit. So our line is a model for the relationship between the number of miles between suburbs and the time it takes to travel that distance in minutes. So in step 7, it says, explain the real world meaning of the slope of your line. So we know slope is equal to change in y over change in x. We know that the slope of our line is 1.27. And since it's not over a number, we know it's over 1. Now, if you go back up to our table, we see that distance is our x value, y is our time. And so distance is being measured in miles, and y is being measured in minutes. Okay? So what we know is, since y is minutes, we know that it takes 1.27 minutes to travel 1 mile. So the representation of our slope is that it is telling us how many miles we can, or how many minutes it takes to travel 1 mile in Chicago. So on average, it takes 1.27 minutes to travel 1 mile between these different suburbs. Now, it then says use your linear model to predict the time it takes to travel 30 minutes. So if we would want to use that model, our model being y equals 1.27x plus 8.15, what we would do is we would take the number 30 and plug it in for x. So when we plug that in, we have 1.27 times 30 plus 8.15. So it would take approximately 46.25 minutes to travel 30 miles. Okay? And then finally it says use your model to predict the distance you would travel in 30 minutes. So in this case, if we wanted to predict the distance traveled in 30 minutes, minutes is our time, so we have, or is our y value, so we have 30 equals 1.27x plus 8.15. We would subtract 8.15, and so 30 minus 8.15 is 21.85. That's equal to 1.27x. And then we would divide by 1.27. And that would give us x is equal to 17.2. So in approximately 30 minutes, you would travel approximately 17.2 miles. Now, in step 10, it says some of your data points may be very close to your line, while others could be described as outliers. What would cause these outliers? So in this case, if we're thinking about driving, some things that might cause outliers are traffic. Maybe you have car trouble. Okay. Maybe you get stuck at a train. So maybe you had to stop and get gas. So again, there might be some things that cause your travel time to be a little bit longer, which could create an outlier. So let's take a look at, so again, one thing to make sure you understand is modeling to fit data can be useful in many situations that involve making predictions. So let's take a look at this example. It says this table shows how many grams of fat and how many calories there are in some hamburgers sold by national chain restaurants. It says write a linear equation to model the data. So again, what we're going to do here is we're going to use Desmos, and we're going to type in that table. And so we have, if we add our table, 24 and 440. We have 8 and 240. We have 52 and 810. We have 93 and 1300. That is a lot of calories for a burger. 56 and 910. We have 19 and 370. 29 and 550. 26 and 520, 69 and 1120, and finally 31 and 580. So let's hit this little plus sign over here and it will show us our points. So there we go. And we want a line of best fit. So again, to do that, you're going to go Y. You're going to hit this little AB down here, AB, sub 1. Notice it tells you there's 10 elements there. We want the approximate symbol, A, X, sub 1, plus B. So you'll see it tells you what your equation would be. Y equals 12.95 X plus 156.89. 156.89 plus 156.89. So it says give the real world meanings of the slope and y-intercept of your line. So the slope, again, change in y over change in x, would mean that you have 12.95. Your y value is calories, so calories per, your total fat is your x coordinate, so per 1 gram of fat. And then your y-intercept would be equal to your starting value. So in this case, that is when x is 0. So that would mean that if there are 0 grams of fat, your burger would have 156.89 calories. So it says predict the calories in a burger with 80 grams of total fat. So if we wanted to do that, we'd have y equals 12.95 times 80 grams of fat plus 156.89. Type that into your calculator. 12.95 times 80 plus 156.89. You get 1,192.89 calories. If we wanted to predict the total fat in a burger with 800 calories, we would have 800 equals 12.95x plus 156.89. We would subtract 156.89 from both sides. So we'd have 800 minus 156.89. That would give us 643.11 equals 12.95x. Divide by 12.95, divide by 12.95, and you would get x equals 49.66. So you have 49.66 grams of fat in a burger with 800 calories. Now, finally, it says, what is the x-intercept and what does it represent in this situation? So if we look at our equation, if we look at our x-intercept, it's right there. So we get negative 12.114 and 0. So we'll say our x-intercept is negative 12.11 comma 0. And so if we use what we look at here, we would know that so this says that if there are, if your burger has 0 calories in a burger, then there are negative 12.11 grams of fat. And so if we had to interpret this, we'd say the x-intercept really doesn't mean anything to us because first of all, you aren't going to have, a burger cannot have 0 calories. And then, you also cannot have negative grams of fat. So in this problem, the x-intercept really is not useful to us. It doesn't give us any information. So in the rest of this chapter, you'll see how to find a line of fit for the data using various forms of linear equations. All right. The thing that you should take away from this is that slope-intercept form is y equals mx plus b. Okay, m is the slope and b is the y-intercept. Okay, so again, how does the slope-intercept form of a line differ from the intercept form? How are these different? The big thing is the variables. Okay, slope here, m equals slope, b equals y-intercept. Over here, b equals slope, and a equals y-intercept. All right. Why would you want to make a mathematical model such as a line to represent a set of data? It's going to allows us to make predictions about the situation. Okay. Finally, it says give the slope and y-intercept of each line. Slope would be equal to 5, and the y-intercept would be equal to -2. The slope here would be equal to -1/2. The y-intercept would be equal to 4. And again, if you want to write the equation of the line using the slope of -2/3 and y-intercept of 1, it'd be y equals m, which is our slope, x plus b plus 1. So go ahead and work on the homework, and if you have any questions, message me on Remind or